Hi, this is a level 2 video looking at the tricky question of whether you can actually fall into a black hole since the speed of light goes to zero at the event horizon. We'll start with the analogy of the AI and the pendulum. Then we'll see that you can sort of fall into a black hole as long as it does not evaporate. We'll also see that no one outside the black hole can speak of the horizon having been crossed in the past tense. Let's get started. If you haven't watched the level 1 videos, I recommend that you do so, especially the third one on slow light. In that video, we saw that time slows down near a black hole, and that if we bounce a light flash off a mirror, the velocity goes to zero near the event horizon, and that the total travel time for the flash can be as long as you like, for example, 1 trillion years. We also saw that this Shapiro delay is a real physical effect that we can measure. It is not just an artifact of the choice of coordinates. With this slow motion effect, this time dilation, we can compare an astronaut far from the black hole
Daisy, Daisy,
and her twin near the black hole who will run in slow motion.
Daisy, Daisy.
And she will experience the rest of the universe as running in fast motion.
Daisy, Daisy.
Daisy, Daisy.
If the astronaut falls toward the black hole, she will initially speed up, but then slow down, just like the light flash. When she approaches the event horizon, the speed goes to zero. And, just like the light flash, our astronaut could, in theory, bounce back at any time and reappear 1 billion years later. So then, can the astronaut ever cross the event horizon? The answer given is usually yes. For example, Kip Thorne writes in an otherwise excellent book, "Does this mean that the infalling robot has not yet crossed the horizon and never will? No, not at all. It flew through the horizon many minutes ago." However, we'll see that this statement is partly incorrect, and that the correct part is only correct in one special circumstance that may not correspond to our universe. To analyze this problem, we'll start with the analogy of the AI and the pendulum. Here's the pendulum. For very small motions, it's linear, and so when we graph the angle against time, we get a sine wave. But for large motions, it's nonlinear. The larger the amplitude, the longer the period. If we place it exactly straight up, it will stay there forever, like a pencil, perfectly balanced on its tip. And if we give it exactly the right amount of speed at the bottom, then it will approach that top position forever, going more and more slowly. These are standard results for a nonlinear pendulum. Now let's build an artificial intelligence, an electronic brain. It's much like a human brain, except it has a clock on board that runs at 10 gigahertz. It has a camera eyeball to look at the environment. It can even produce audio.
Daisy, Daisy.
If we slow down the clock to 5 gigahertz, the AI will run in slow motion.
Daisy, Daisy.
And it will think that its environment has sped up. Now let's put the AI on the pendulum.
Daisy, Daisy.
But instead of having a constant clock rate on the circuit board, we let the clock tick every time the angle of the pendulum changes by some tiny amount, let's say a micro arcsecond. Then, at the bottom, when it moves the fastest, the clock rate will be fastest, and it will be zero when it turns.
Daisy, 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 Daisy.
We can think of the laboratory as having a time coordinate little t, and the AI having its own local time coordinate, capital T, similar to the earlier video on slow time. This local time can be called proper time or wristwatch time, which is how the AI experiences time. The laboratory time, little t, ticks at a steady rate. But the proper time varies and sometimes ticks very slowly. Now, when the pendulum is given just enough speed to approach the top forever, there is a fixed number of micro arcseconds, a fixed number of total clock ticks that will ever occur for the AI. like the astronaut approaching the event horizon.
Daisy.
The AI's time coordinate, capital T, stretches out to infinity. He freezes up. There is a maximum value of capital T, 10 in our example. According to someone in the laboratory, the AI never arrives at 10, not this side of infinity. So, does the AI reach the top and continue down the other side? Well, mathematically, you can simply map little t infinity to capital T10. Let's grab onto infinity and 10 and pull them down. The little t marks bunch up, and the capital T marks become evenly spaced. After this, you can extend capital T beyond 10 and let the pendulum continue on the other side. Let's change video time from little t to capital T, the way the AI experiences the ride. The pendulum then moves at a steady rate.
Daisy, Daisy.
Between 9 and 10, it will see the stars burn out, then continue from 10 to 11, singing and thinking its thoughts.
Daisy, Daisy.
After 10, there is no longer a mapping to little t. No one in our universe will ever be able to say that the AI has gotten to the top. Let's go back to our astronaut. Her situation is very similar to that of the AI. Her proper time, capital T, slows down to 0, while an infinite amount of little t goes by. Her own time is limited to a finite capital T, let's say 10. Let's get rid of the z coordinate and replace it with little t as in previous videos. As a footnote, let's point out that because she's moving relative to space, her time runs even slower than for someone sitting still at a fixed point. This we saw in the video on special relativity. She gets a total of 10 time sticks. Meanwhile, far from the black hole, the time sticks are short and we have an infinite number of them. For the astronaut, the last time stick stretches out to infinite little t. Does it stop there? Well, not necessarily. As with a pendulum, we could grab onto infinity and pull down on time. Let's stack some hypervoxels so we can see space-time compress. As we pull down, notice the compression in both time sticks and hypervoxels. It's as if we look from some external reality, and in that reality, space compresses infinitely at the upper edge. And with this compression, the time sticks of the falling astronaut are finite, and she can now progress to capital T equals 10. We could then imagine that where the black hole is located, someone in the external reality adds on some space-time where the black hole is, past infinite little t. There will be a post-infinity extrusion that cannot send signals to the rest of the universe. So in that sense, the astronaut could keep falling past the event horizon and into the post-infinity extrusion. If you're familiar with Kruskal-Sekaresh coordinates, this post-infinity extrusion is known as region 2. Does this sound hokey? Maybe, but it's consistent with the mathematics of general relativity and with our visualization of space-time as hypervoxels that deform. However, we should make two important caveats. The first caveat is that someone outside the black hole cannot say that the astronaut crossed the horizon some minutes ago. For one thing, we saw that the astronaut could in theory bounce back out at any time before crossing. Also, for someone to say that an event E has already occurred in the past tense, he must be inside the event's light cone. Let's look at the black hole with T running upward. Here we have an event E, and it has a light cone. If an astronaut is inside the light cone, she can say that the event E has happened in the past. But at the event horizon, the light cones tip over. Someone outside the event horizon cannot be inside that light cone, so she cannot say that the event E has already occurred some minutes ago. The second important caveat is that black holes may evaporate and disappear, according to Stephen Hawking. This happens in finite time. It happens very slowly, so in the video, our time coordinate little t is not to scale. It is large, but not infinite. Let's see what happens to our astronaut. When the black hole evaporates, it loses mass, and so the radius shrinks. But the space-time outside continues to be a Schwarzschild space-time, with the speed of light being 0 just outside the shrinking event horizon. So the astronaut would keep falling toward the receding event horizon, but remain just outside, where the speed of light goes to 0. So, to summarize, if a black hole does evaporate, then no, you cannot fall into a black hole. You may then ask, if an astronaut cannot fall into an evaporating black hole, then what about the particles in a collapsing star? That's how we think black holes would form. So can a black hole be created in the first place? This is a very good question, and we'll analyze it in a separate video. For more videos, go to physicsisnotweird.com, and I'm Eyvind Bernander.